So in the last session, we have been talking about homomorphism as a tool to compare two groups. Well, homomorphism is a very weak tool to compare uh, two groups, because we have seen that um, the groups doesn't need to be of the same cardinality. Like um, you can define a homomorphism from Z to Z3. So this is a totally an infinite set, and this is a finite set of order 3. But still we can define a homomorphism from Z to Z3. All we are interested in this case is to make sure that the elements in two groups behave similarly. But we have a much stronger tool based on this homomorphism. We can refine the homomorphism to make it as a stronger tool, and that is called the isomorphism. Isomorphism. So the definition is like this: a homomorphism from G to G prime is an isomorphism if it is bijective. For example, here we can still define a map like this: phi from 2z, C to 2z by phi of n is equal to 2n. This is a homomorphism. This is actually this phi is homomorphism, and this phi is onto, and this phi is 1, 1. So that means this shows that this is a bijective map. So C and 2C are isomorphic. So we can say that if there exists an isomorphism between the groups G and G prime, then G is isomorphic to G prime, and vice versa. Because if it's a bijective map, its inverse is also an homomorphism, and it's a bijective map, so inverse is also isomorphism. So here you have 1, 0, 1, 2, 3, 4, -1, -2, etc. This is our C. Our 2C is actually equal to 0, 2, 4, 6, -2, etc. Even though we see that there are some missing elements here, we can still define a homomorphism. This is actually 1, 1, and onto. That is because these are infinite sets. In the last session, we also discussed about a special subgroup based on homomorphism, and that is called kernel. So if phi is a homomorphism from G to G prime, then kernel of phi is equal to the inverse of the identity subgroup of G prime. Or you can say this is equal to elements from G that are mapped to the identity of G prime. And we also showed that phi inverse of phi of A is equal to AH or HA for all A in G, and H is equal to the kernel of phi. So this is a special subgroup of G in the sense that if you take any element A in G, the left coset and the right cosets are same. So there may be some other subgroups other than the kernel. Kernel is a subgroup, but if you generalize this idea for any subgroup, we call that subgroup as normal. So definition is a subgroup H of G is normal if AH is equal to HA for all A in G. Kernel is one of them. Kernel is actually based on a homomorphism. We constructed a subgroup of G based on this homomorphism, and we found that this property is true. So kernel of any homomorphism is normal. But in case, if you generalize that idea to any subgroup which satisfies this condition, we call that subgroup as normal. So corollary is if phi from G to G prime be a homomorphism, then kernel of phi is normal. When we say that AH, the left coset, is equal to the right coset, this does not mean that, this definitely does not mean that AH is equal to HA for all H in H. This is not does not mean this. All it says is if you take a H here, H1, and if you take there, you can find an H2 here such that they are equal. For example, if you found that kernel of a homomorphism is normal, we'll see another example here. Let's say we define a map from Sn to any set and any group by phi of sigma is equal to E prime of or E of G. You know that this is a trivial homomorphism. So what is the kernel of this? The kernel of this is equal to Sn, because the whole Sn is mapped to a single element. So the inverse of that single element is the whole of this. So kernel of phi is Sn, and Sn is actually non-abelian. So that means if you take sigma 1 or sigma times Sn, this is our H now, does not need to be Sn times Sn of sigma or what it means here is sigma Sn is equal to Sn sigma. That does not mean that if you take an element here, let's say mu, and here it is mu sigma. These does need to be equal. If you take a mu here, we'll find another mu here so that they are equal. That's what this says. So this will be mu1 and this will be mu2. This is a group, subgroup, not a single element. So as a group it commutes with the other elements of the group, but if you take an individual element, that may not be commutative. So that is the idea of normal. This is very important in constructing factor groups. Now we'll go back one step behind to permutations. We want to establish one more important theorem. The reason why I didn't do it when we did permutation is because that time we don't have the isomorphism tool. So we are going to use the isomorphism tool to establish a theorem here. It's called Cayley's theorem. Is that any group is isomorphic to a group of permutations. Group of permutation means this does not mean that it is a whole of symmetric group. It's a subgroup of a symmetric group. Meaning that group contains permutations. That's all it says. So what we need to do is we need to define a homomorphism, a bijective homomorphism from a group to a group of permutations. So let G be any group and SG be the group of all permutation on G. Well, permutations means it's a bijective map from G to G. So now we need to define a map from G to SG. That does not need to be an onto, but it could be onto a subgroup of G. So what we do is here the element is here if you have to take an element from G and that should be mapped to a permutation here, and this permutation is a bijective map from G to G. So first let us define a permutation that we are going to consider. So let X belongs to G. Then define lambda X from G to G by lambda X of G is from G is equal to Gx. Now our claim is this lambda X is a bijective map. So lambda X is a bijective map from G to G. Once you prove that lambda X is a bijective map, what does that mean? Lambda X belongs to SG. So how do you prove this? So what we need to do first is, we need to do it's onto. Lambda x is onto because we take an element from G, and we need to show that there is an element here that is mapped to C. So what we do is lambda x of G inverse, sorry, lambda x of C times x inverse. C times x inverse. What is this? By definition it is, this is Cx inverse times x, and that is C. So for every C in G, there is an element in G such that lambda x is mapped to that element. So the lambda x is onto. Lambda x is 1, 1. Because let's take two elements a comma b in G and assume that lambda x of A is equal to lambda x of B, and that implies AX equal to x equal to bx, and that implies A equal to B. So lambda x is 1, 1. That means lambda x belongs to, that implies lambda x belongs to S of G. Now, see, this is an arbitrary element in G. Now we will define a map. Define phi from G to SG by phi of x is equal to lambda x. So now we need to prove that phi is a homomorphism and phi is bijective. So let's first find phi's homomorphism. How do you prove phi is a homomorphism? Take two elements from here. So phi of xy is equal to lambda xy. And what we do is phi of xy of an element, because this is going to be a bijective map on G. So of A is equal to lambda xy of A, and that is equal to xy of A, and that is equal to, now it's going to be AXY. It's going to be AXY. AXY. And that is equal to AXY. And that is equal to lambda y of AX. And that is equal to lambda x of lambda y of A, and that is equal to lambda x times lambda y. So this is a homomorphism. Now we have to show that it's a bijective map. So let's say, so phi is onto. We don't need to show that phi is onto, because we are going to consider the image of phi. So let us not use, we don't need to use onto. See, we are going to consider phi from G to SG, and we are going to consider the the subgroup of SG that are mapped onto G only. So that is always will be onto. So we are not taking the whole of SG. So all we need to do is phi is on 1 1. Phi is 1 1. So how do you prove phi is 1 1? See, let us say phi of x is equal to phi of y for some xy in G. That implies lambda x is equal to lambda y. Okay, now what you do is let us take lambda x of E is equal to lambda y of E, because lambda x and lambda y are same. So this is actually equal to Ex is equal to Ey, and that implies x equal to 1. So that means phi is bijective. So phi is a homomorphism. So that means G is isomorphic to phi of G, which is a subgroup of SG. SG is a group of all permutation on G. Phi of G is a subgroup of G, and we showed that this phi is an isomorphism, where phi of x is equal to lambda x, defined by this, and that is a proof for Cayley's theorem. Very powerful theorem, because it is actually making a isomorphism from any group to a group of permutations. We are going to complete this session on homomorphism after doing some problems. So let us do the first one. It seems it's going to be a very easy one. It's a very trivial one, but it is not so. Let G be a group, then define phi from G to G by phi of G, phi of A is equal to A inverse for all A in G. We might think that this is a homomorphism. So we want to find out, so our objective is to prove or disprove whether this is a homomorphism. Definitely this is a 1-1 and onto map. Well, then is it homomorphic? Let us see. So what you do is take two elements, A comma B in G. So phi of AB, we want to prove that if it's a homomorphism, we want to prove that phi of A is equal to phi of AB is equal to phi of A times phi of B. But what is this? This is actually equal to AB inverse, and that is equal to B inverse A inverse. And phi of A times phi of B is equal to A inverse times B inverse. They are not same unless G is an abelian group. So phi of AB is not equal to phi of A times phi of B if G is a non-abelian group. So if you want to make phi a homomorphism, then G must be an abelian group. But if G is an abelian group, then phi of A is equal to A inverse is a homomorphism. Now let us do a computational problem. So let phi from C to C7 be a homomorphism defined by phi of 1 is equal to 4. Find kernel phi. There are a couple of things we want to notice here. We haven't completely defined the map. Actually we did, but if you don't say it is a homomorphism, this particular data is not sufficient enough to define a map like this. It says that it is a homomorphism. If you just say phi is a map defined by this, then this is not a map at all. This becomes a map because of it is homomorphism. Reason for this is, see, when you are defining a map, every element of C should be mapped to some element of Z7. Here we are actually mapping only one element of this. Then, because this is a homomorphism, we can compute the values of the other elements of Z. Why? Because the C is actually generated by 1. Meaning every element of C can be expressed as a finite sum or finite binary operations of 1. For example, 8 is equal to 1 plus 1 plus dash dash 1 8 times. So phi of 8 is equal to phi of this. And because this is homomorphism, we can write it as phi of 1 plus phi of 1 plus phi of dash dash phi of 1 8 times. So it's a valid map. If it is not a homomorphism, this is an invalid map. It is not a function at all. So what we need to do is we need to find out the kernel. So we will write it like this: Z and C7. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. Here 0, 1, 2, 3, 4, 5, 6 and 7. And here minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, etc. So phi of 0 definitely is going to be to 0 because it is a homomorphism. Phi of 1 is going to phi of 1 is going to 4. Where does phi of 2 go? Phi of 2 is equal to phi of 1 plus phi of 1 is equal to 4 times 4 plus 4. And that is equal to 8, and that is equal to 7 mod, that is equal to 1 mod 7. So 2 goes to 7. What about 3? See, what we need to do is we need to find out all the elements from C that are mapped to 0. So phi of 3, I am going to write only up to this, then we'll find out straight away the elements of Z that is mapped to 0. This one is going to be 1 plus 4. This is 5, 2, then another 1, so this will be 5. So 3 is going to be to 5. When you go like this, phi of 7 is going to be 4 plus 4 plus dash dash plus 4 7 times, and that is equal to 0. So 7 actually goes to 0. In fact, all the multiples of 7 should go to 0. So phi of 14, phi of 21, etc., and phi of minus 7, etc. will go to 0. So the kernel of this homomorphism, is 0, 7, 21, etc., and that is nothing but 7. 7C. We'll do another computational problem. Let phi from C cross C to S10 be a homomorphism defined by phi of 1 0 is equal to 3 5 2 4, and phi of 0 1 is equal to 1 5 6 10 8 9. Then our problem is compute or find kernel of phi. First I want to make sure that this is a valid map. See, C cross C is generated by 1, 0 and 0, 1, because any element of C cross C, let us say m times n, that can be written as 1, 0 plus dash dash 1, 0 m times, and n can be written as 0, 1 plus dash dash 0, 1 n times. And because this is a homomorphism, see, our idea is to define every element of C cross C to S10. So any element of C cross C can be written like this. And because this is a homomorphism, phi of this will become phi of this. And that is equal to phi of 1, 0 plus dash dash phi of 1, 0 plus a phi of 0, 1 plus dash dash phi of 0, 1. Because this is a homomorphism. And you know the values of each and every element. So you can compute the value of mn. And that is why I've said this is a valid function. If this is not a homomorphism, these two mapping is not sufficient enough to define this map. Now we need to compute the kernel of that phi. See, it is going to the symmetric group of or group on 10 elements, and that is, these are actually permutations. These are not coming from here. These are all permutations. This is a transposition and this is a transposition. And this is a transposition and this is a cycle. So, what we need to do is find m and n such that phi of m comma n is equal to the identity map. And we know that C of 0 goes to identity map. Identity permutation, sorry, identity permutation. Or I'll write it as I. This is actually identity permutation. If we can find this m and n, then our answer will be, kernel of phi will be MC cross NC. So this, see, how do you find this? So we need to find this map, the order of this map, so that this could vanish. We need to find out, so what is the order of this? The order of 3, 5, 2, 4 is equal to 2, because both of them are transpositions. And the order of 6, 10 or a 1, 5, 6, 10, 8, 9 is equal to 4. Because this is 2 and this is 4, so the LCM of this is 4. Now, see, if you take an element from here, like phi of m comma 0. See, we'll write it like this. So we need to find out phi of m comma n is equal to phi of m comma 0 plus phi of 0 comma n. This m, so this has to be the identity map. So this will become 0 whenever m becomes a multiple of 2. And this will become 0 when n becomes the multiple of 4. So this happens when m becomes the multiple of the order of this 3, 4, 3, 5, 2, 4. And n becomes the multiple of the order of 1, 5, 6, 10, 8, 9. So that means the kernel of phi is equal to 2c multiple of 2 times 4c multiple of 4. If you want to verify this, we'll take an element phi of 6, 4. This should be equal to the identity map, because 6 belongs to 2c, 4 belongs to 4c, So this should map to the identity map. This definitely will go to identity map because this is equal to 6 times phi of 1 0 plus 4 times, this is actually off because you are this is a permutation, so this will be 4 times phi of 0 1. So this is a identity map on after another identity map, and that is equal to identity. And if you take any other element other than this, you are not going to hit this. So the kernel of phi is 2c times 4c. To do another problem, how many onto homomorphism are there from Z to Z? It's very simple. So if phi from Z to Z is an onto homomorphism, then phi should, or the phi of 1 should map to a generator of C, this C. See, this is the generator of the source, and this generator I am talking about, this generator of the image. If this is not a generator of this C, then it cannot be onto. So what are the homomorphisms of homomorphism, so the onto homomorphisms are either phi of 1 is equal to 1 or phi of 1 is equal to minus 1. These two has to be generator of this. There is no other generator. So this means the homomorphisms are phi of n is equal to n or phi of n is equal to minus n. So there are only two onto homomorphism from Z to another problem. Find the values of G in G such that phi is a homomorphism. Phi of A is equal to GA for all A in G. That is one problem. Another problem is phi of A is equal to G A G inverse for all A in G. See here, this is very clear. You want to find the value of G so that this is a homomorphism. So if this is a homomorphism, phi of E should be equal to E, and that implies GE is equal to E, and that implies G is equal to E. Here, if you want this, here that you are taking a different property. We'll take two elements from here. Phi of AB, if phi needs to be a homomorphism, this has to be phi of A times phi of B. Phi of AB is what? G of AB J inverse by definition. And this is actually G of A G inverse G of B G inverse. And that is equal to A G of AB J inverse. And that implies for all G in G, phi is a homomorphism. If you take any G, this will become a homomorphism. So those are the values. Here G is equal, G must be equal to E, but here G can be anything. We will do another problem. Let phi from G to G prime be a homomorphism and G is finite of prime order. Then phi is either trivial or 1, 1. So G is a finite set. So we know that the kernel of phi is a subgroup of G, and the order of a subgroup divides the order of the group. So that means order of kernel of phi is a divisor of G, divides the order of G. Implies kernel of phi is equal to 1 or P, where P is a prime. When kernel of phi is equal to 1, that implies phi is 1, 1. When kernel of phi is equal to P, that implies is trivial. Kernel of pi is equal to P means all the elements of G is mapped to the identity element of G prime. So it is either 1, 1 or trivial, and that's what we want to prove. We will do another very simple but very important result. Let phi be a homomorphism from G to G prime, and mu is a homomorphism from G prime to G double prime. Then mu after phi is a homomorphism from G to G double prime. It's very simple. phi from G to G prime is a homomorphism, implies phi of xy is equal to phi of x times phi of y for all x comma y in G. Mu is a homomorphism G prime to G double prime, then mu of AB is equal to mu of A times mu of B for all AB in G prime. So we'll take mu of phi of xy is equal to x times y is equal to mu of phi of x times phi of y, and that is equal to mu of x times mu phi of y. That implies mu phi is a homomorphism from G to G double prime. We'll do our last problem in this session. It is let phi is a map from G to G prime. Then phi of G is abelian if and only if for all xy in G x inverse y inverse xy belongs to kernel of phi. So how do you prove that this is an abelian group? Take two elements from here and compose or multiply and see that it is commutative. So let us take two elements. Let x prime, y prime belongs to phi of G, and that implies phi of x equal to x prime, phi of y is equal to y prime for some x comma y in G. So phi of G is abelian if and only if x prime y prime is equal to y prime x prime, and that is equal, that implies or implied by y prime x prime inverse x prime y prime is equal to E prime, where E prime is the identity of G prime. And that implies this is what? This is actually x prime inverse times y prime inverse times x prime times y prime is equal to E. So this is actually implies and implied by. And what is this? This is actually phi of x inverse times phi of y inverse times phi of x times phi of y equal to E prime. implies and implied by, if and only if. This is actually phi of x inverse, phi of y inverse, phi of x, phi of y is equal to that. And that implies and implied by phi of x inverse y inverse x y is equal to E prime. And that is implies and implied by x inverse y inverse xy belongs to kernel. And that's what we want to prove.